classes that have come from physics have come to take this another properties of matter, and it's a so I'm taking the mechanical properties that handle something called Hooke's law as a subtopic. So it was introduced by someone called a scientist called Hooke. He stated Hooke's law as the extension of an elastic material is the net proportion to the force applied, provided no elastic limit is exceeded. So important things to note in that law. Let me first write that law. So that's the definition. That's the says that the extension of an elastic material is direct proportion to the force applied, provided no elastic limit is exceeded. But within our law, there are some things to note, all which are important in our definition. So we have the extension of an elastic material is directly proportional to the force applied and provided no elastic limit is exceeded. So there are so many things to note within this law. And one, we need a force and an elastic material. And the elastic materials we have a rubber band, the springs, and so on, something that is elastic. So when we think of an elastic material, that's a material that once we apply force onto it, it regains its original shape and size once the force is removed. So, and the example is the rubber band. The rubber band, how they behave, and the plastic spring. So, there are so many. But now, in our law, we talk about we say extension is direct proportional to the force applied. The force is direct proportional to the extension. So when the force is increased, then the extension has to increase. So meaning if you have an elastic material and you apply a force onto it, so the moment you increase the force, the extension of that elastic material has to increase as well. So the more the force increases, the more the extension increases. That's the meaning of proportionality. So mathematically, once you want to remove this proportional symbol, you create a constant. So since we create a constant, this constant is not a real constant, it is a physical constant called a constant of proportionality. It's a proportionality constant. So the K will be constant exists out of extension, whereby the constant inside the meter and the extension, the assignment of extension is meters. So hence we shall get the assignment of a constant of proportionality, which is K. So assignment of K is Newton per meter, since the force is Newton and the extension is meter. So the constant of proportionality, the assignment is Newton per meter. So we can do an experiment to verify the experiment whereby we shall need this constant. So since this is a new curriculum, we shall need to have a scenario relating that. For instance, let me create a certain scenario whereby there is a certain girl in senior year. So she goes to a garage and finds a toolbox, but within a toolbox she finds a spring in that toolbox. Then that spring is labeled K, having 45 kilograms on that spring. Then she fails to get to know what that means. Then she takes that spring to a senior to class and tells them how to find that K. So once you find that, then having found that toolbox, within a toolbox there is a spring and the spring is labeled K as 45 kilograms per meter, meaning that's the spring constant. So we are required to find that spring constant. So we shall use the box here, experiment the box here to come up with that. But whenever we are doing that experiment, there are so many things we need to know. One, we need to know the volume of that spring. We need to know the aim of the experiment. What is the experiment all about? What do you need to verify? What do you need to determine? So, we need to know the aim of the experiment. So, we need to know the aim of the experiment because that's okay, let's start it. Apparatus. You need to know which apparatus that are you going to use according to the experiment that you are going to do. So then we need to know the variables of the experiment. You need to know the variables of the experiment. What determines the experiment? We have the independent variables, we have the dependent variables, and the controlled variables. So those are the difference, those are three variables we need to know. The independent variables, the dependent variables, and the controlled variables. Then what else do we need is hypothesis. What value are you expecting to get? So that's what we call the hypothesis.
siya lang.
So that is the expected value to get. Then from there, you need to know the procedure and the setup. So having known the procedure, meaning you know what you are doing. So you need to write the procedure. So you need to know what you are doing. So you write the procedures, you build a setup. So meaning that you know what you are doing. So another thing to note is you need to do the table of results and go to the graph. Doing the graph work, we shall need to know the slope. So we shall need to know the slope of the graph. Then after knowing the slope of the graph, since we are aiming at gauging the KP, so our slope, our graph will be a form the graph of mass and then its extension, whereby our slope will be our constant K. So after knowing the constant K, which is the slope of the graph, then we need to draw a conclusion and even. So actually, you need to know whether you have successfully done well or there are some errors made in the exam. So you need to know. You need to know the source of the errors. If there are some errors, then what are the precautions you need to do such that errors is there. And then after knowing the precaution, the errors, then you need to know the precautions how to overcome those errors. Then you can draw a conclusion. The expected value you wanted to get is that or not. And then secondly, so this is the rough one of the experiment. So number one. Our involvement is better. Our aim is to determine the skill constant. Then, having known the aim of the experiment, then the apparatus is. The apparatus is we need to have a rate of scan. We need one screen. We need 6 mouses. We need 1 meter. Then we need a 4 meter. That's all that we need to do our experiments. Then after doing that, then what are the values? Okay, let's first start with the values. I think this is last the expected value. Okay, which is now the last case. So, having seen those SIs, our graph is going to be a mass. Since this is SI because a mass and again it's extension. Since the SI extension is not so our slope is going to be a mass against extension. So after the hypothesis, then we talk about the variables, the dependent variables and the dependent variables. So the dependent, according to the apparatus, we will have an experiment that we are going to do. Which one depends on the other and which one is independent of the other than the one that controls the experiment. So those are the variables. So when we go to the procedures and the setup, let us have a setup. So that's a little stand. Then that's a meter rule. Then we need to have this is a coin. Then this is that's a spoon. Then those are the masses. Then having the foot up there, meaning you know the procedure. So what we shall need to we have a little stand. Then on a little stand, you clamp a meter rule. So after clamping the meter rule onto the little stand, then you put a spring onto the little stand stick. Then and the spring should have a pointer for easy reading from the meter rule. Then start inserting masses onto the spring one by one. So after putting the mass, then you expect some extension into. Then you note the extension. So you need to have the initial extension. Assuming after doing the experiment, the initial extension will get set to 5.6. And should be in centimeters since we are reading from the meter rule. Should be in centimeter and then should be to one decimal place. Then after getting the initial position of the initial length of the spring, then you insert the mass, say, 100 gram mass into the spring, then you note the extension, set to 1. Then at the end of the day, we need to get the extension, and the extension is you get the new length minus the original length. Say our extension is P. So it is the new length minus the original length. So for this case, we shall have after having the value in there, should be to one decimal place first of all, and if it is in centimeter, then we shall change it to meters. If the extension is meters, then we shall repeat procedures. So when you see repeat procedures, you keep adding more masses, different masses. At the moment you put masses, you keep on getting the extension. So at the end of the day, we shall have a table of results which will look like this. shall have masses 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. So having such a table, then we need different extensions because we've been doing this experiment and getting different extensions. So assuming here you get 7, decided with our initial extension, first one was 42. Assuming that's your values that you will get in the extensions. So we shall have our figure was 35.6. So the initial position, the initial input of the screen was 35.6. Then we keep subtracting it from the key ones. So we keep having these values, then later you bring them to meters. Then after we shall need to plot a graph, and the graph it will be a mass against extension. So it will be a graph of mass against extension. So indicate the signs in brackets. Then you get different values. You plot the values of mass against extension. So for the mass, and so then this side also gets some values of extension. Then at the end of the day, you start plotting. When you plot, you may have some values like that. And then after you draw a line of this, so you need to use a ruler. Then after you draw a line of the speed, then you get a slope of your graph. And the slope you need to enclose all the plotted values. So this is a change in mass, and this is a change in extension. Then at the end, then we need to get a slope. So the slope, a change in the y-axis, which is a change in mass, also a change in extension. Then at the end of the day, you have your value of k, which is the same concept that we've been looking for. Then after having it, then you identify some sources of error while you are failed to get the hypothesis or the expected value. Then at the end of the day, you look for implementing precautions. Then after you draw a conclusion. So that's how we shall get the spring consonant. Then, since this technique is right, then I'm going to take you through some more other things. But that is specify how you get the spring consonant or verify it slow. Then, some other thing to talk about in this topic, we are going to talk about the tensile stress, the tensile strain, the other and so on. So, so those are the things that we are going to talk about from today, but having known the definition of tensile stress or the formula, okay, from the formula you can get the definition of those terms. So, from the formula, tensile stress is force out of sectional area. For the tensile stress, it is extension out of the normal area, and for others, it is stress out of the strain. So if you know those, if you know their formulas, then the formulas will get the definition. So the definition of tensile stress, it is the first unit cross-sectional area, and then the definition for tensile stress is the ratio of extension to the original end of the material, and the definition for Young's model as the ratio of stress to strain. So since this is physics and this, we know we need to have SI those terms or these terms. So the SI stress rule is the SI force is newtons and the SI area is newtons squared times the area. The SI unit will be newton per meter squared. Or else we shall call it Pascal. That's another term or another sign to call it. So in the SI of tensile stress, it will have no SI unit. Since this is a ratio, and the second SI unit of extension is mass, and the SI unit of the SI unit of extension is meters, and the SI unit of length is also meters. So at the end of the day, when it comes to out, then one does move just the ratio of stress to strain. Since the SI unit of stress is newton per meter or Pascal, and the strain has no SI unit, then the Young's model has the SI unit of stress, then to newton per meter squared, it will give us. Then we are going to have some calculations for this. So we are going to start with the calculation of tensile stress and tensile strain, then later we go to Young's modulus. So assuming you have the deposit of mass 500 kilograms, then and has a cross-sectional area of say 2 meters squared. So the mass which is 50 kilograms and the area of 2 meters squared. So from here we can get the strain. So since we know that force is mv, we shall have a force which is 50, and the v is acceleration due to gravity. We know it's always stable. So this is 500 meters. So don't forget to put the SI. So it's 500 meters. Then the area will be as that. So our strain will be stress. That's our which will be 500 out of 2 meters squared, which at the end of the day will be 50 meters per meter. Okay, so let's come into an example or calculation of strain. Then once we go to that strain, we shall pose a question and say have an elastic material should be elastic because we should, if it is not elastic then we shall not be able to obtain the extension. Then should we have an elastic material originally says 1 meter and has until you apply the force of weight and extends say 0.5 meters. So at the end of the day we shall have the formula of tensile stress as extension out from the beginning, and extension will be now 0.5 out of 1, which will be 0.5. So it has no SI units. We already said that. Then we will have the other formulas. So it will be the other formulas. Squaring out of space. So it will be now this 200 divided by 0.5. So in simple terms, this is 250 divided by 5 out of 10, which will be now 5,000 squared. So that's the Yagazon units. So that's the Yagazon as I think that's what I prepared for you to do. Then, if I don't have some questions, you can reach out to me or you can do it from my office. Then, allow me to stop here for today. Have a nice day.